Hello and welcome to another episode of Literature Talk. Today we have with us Subhayan Aich. He completed his MSc from University of Calcutta and is currently working as a junior research fellow at ISC Bangalore. In today's presentation, he'll be discussing a fascinating and impactful area of research, dealkenylative transformation in organic synthesis. So Subhayan, welcome to the talk and the screen is yours.
Thank you, Bhaiya, for your kind introduction. So, directly going to my presentation. Today, I am going to present on the topic known as dealkenylative transformations in organic synthesis. So, I have divided my presentation into four parts, starting with the introduction, followed by applications. Then I will summarize my presentation, finally wrap it up with the future outlook. In the introduction, at first, I would like to talk about alkenes. Alkenes are one of the most versatile and synthetically valuable functional group in the organic chemistry. Its presence in various medicinal compounds such as cefixime, quinidine underscores its medicinal importance. Is the second most encountered functional group among the natural products, and from the industrial point of view, these alkenes serve as feedstock chemicals forming the backbone of large-scale synthesis and manufacturing process. Given their widespread occurrence and intrinsic reactivity, the alkenes have been widely investigated as strategic platform for molecular remodeling and structural diversification. Alkenes undergo a broad spectrum of reaction. In the classical approach, it can undergo the ozonolysis metathesis involving the CsP2-CsP2 bond cleavage. It can also undergo cyclopropanation, epoxidation, diverse difunctionalization reaction harnessing the pi bond activity. More recently, the selective CsP2-CsP3 bond scission has emerged as a powerful strategy for construction of structurally complex architectures which are otherwise hard to construct. So with this background in mind, my presentation will be focused on the selective CsP2-CsP3 bond scission of unactivated alkenes, particularly in the context of the naturally occurring scaffold to synthesize a large pool of chiral organic compounds. Also, I will highlight how this methodology adds elegance to the retrosynthetic approach. For the limpid overview of the methodology, at first the alkene undergoes activation, forming the ozonide using molozonide using the ozone. Now the molozonide undergoes rapid deconstruction, forming the Krieg intermediate. Now the Krieg intermediate can be trapped using methanol to the alpha methoxy hydroperoxide, and now this alpha methoxy hydroperoxide species can be subjected to various functionalization reactions. So whatever I am going to present in my latter part of the presentation, this mechanism will be very much important, and this activation is the key tool for the dealkynylation strategy. Historically, in 1964, Shinji Murai used the strategy for the first time on octene to synthesize dodecane derivatives. Later in 1980, Professor Stuart Shiver reported the synthesis of enantiopure substituted alpha-beta unsaturated cyclohexenone from the naturally occurring dihydrocarbon using the dealkynylation. Later, this methodology is diversified and explored by Professor Stuart Shiver's postdoctoral student, Professor Mohin Won, and she explored the strategy more and enabled the synthesis of natural product derived complex architectures. Having discussed about the mechanistic foundation and historical development of this methodology, now I will move to its synthetic applications. In the application of the CsP2-CsP3 bond scission, I will highlight how this methodology enables the editing of complex molecules and synthesis of valuable architectures. And I will start with the simplest functionalization using hydrogen known as hydrodealkynylation. In the hydrodealkynylation, the alkene is first activated using ozone and methanol to the alpha methoxy hydroperoxide. Then it can be reduced using ferrous sulfate, and thiol is used as a hat reagent to give the hydrodealkynylated product. This methodology works well with monocyclic natural products such as isopullazole dihydrocarbon, bicyclic Wheeler-Michel ketone, and polycyclic terpenoids such as betulinic acid, giving good to excellent yields. In the mechanism, the alkene undergoes activation first in presence of ozone and methanol, forming the alpha methoxy hydroperoxide species, the intermediate one. Now, the ferrous can reduce it to the alkoxy radical, which can push back and kick out one alkyl radical. And the alkyl radical now can take an hydrogen atom from the thiol to generate the desired hydroalkynylated product. After the hydrodealkynylation, I will focus on the heteroatom incorporation in the core natural products, and I will start with the oxygen, the oxodealkynylation. In the oxodealkynylation, in the similar methodology, the alkene is first activated to the alpha methoxy hydroperoxide, followed by reduction using ferrous sulfate, and tempo is used as a radical quencher to form the tempo ether. Now the tempo ether can be oxidized using magnesium bis monoperoxythalate to the desired keto product. In the substrate scope, we can see that monocyclic natural products such as carbiol oxide, dihydrocarbon, phosphorus containing limonene diol, and bicyclic nutcatone gave good to moderate yields. In the mechanism, the alkene is first activated to the alpha methoxy hydroperoxide, which can be reduced by the Fe2 species to the alkoxy radical. Now the alkoxy radical undergoes beta session, forming the alkyl radical. The alkyl radical is now trapped by the tempo, forming the tempo ether, the intermediate 3. Now the tempo ether can be oxidized using MMPP, forming the desired keto product. Now I will be discussing the thiodealkynylation. This strategy has its unique significance as sulfur plays a vital role in various antibiotic antifungal agents. So the thiodealkynylation works similarly in the first step of the activation step using ozone and methanol to the alpha methoxy hydroperoxide. Now the ferrous sulfate reduces this species and diaryl disulfides are used as sulfur source to generate the desired thioether products. In the examples, we can see the monocyclic natural products such as limonene, isopullazole, bicyclic nutcatone, and polycyclic complex terpenoid betulene gave moderate to good yields. So mechanism, the alkene undergoes activation via ozone and methanol to the intermediate one, the alpha methoxy hydroperoxide. The alpha methoxy hydroperoxide is then reduced via the ferrous complex to the alkoxy radical, which undergoes beta session to generate the alkyl radical. Now there is diaryl disulfide. The alkyl radical can take the sulfur from the diaryl disulfide, forming the desired product and the sulfur radical, which can further go dimerization and the reaction can proceed further. Now it's time to discuss the halogen atom incorporation in the dealkynylation strategy. At first, the alkene is activated using ozone and methanol, forming the alpha methoxy hydroperoxide, which now can be reduced using the catalytic amount of ferrous sulfate. And vitamin C in this case is used as an external reductant, and tosyl chloride or N-bromosuccinamide or N-iodosuccinamide is used as the halogen source to get the desired halogenated product. So this reaction works with chlorine, bromine, and iodine as the halogens, giving moderate to good yields. In the mechanism, in like the previous cases, the alkene undergoes activation via ozone and methanol to form the alpha methoxy hydroperoxide. Now the ferrous reduces this intermediate to itself into the ferric form and generation of the alkoxy radical. Now the vitamin C comes in the play and it reduces back the ferric to the ferrous form, closing the iron catalytic cycle. Now the intermediate 2, the alkoxy radical, which undergoes beta session to generate the alkyl radical, the intermediate 3. Now there is the halogenating reagent and the alkyl radical takes the halogen from that species, forming the desired halogenated product. Finally, I will conclude the halogen atom incorporation by discussing the amino dealkynylation strategy. In the amino dealkynyl strategy, the alkene undergoes activation as first, forming the alpha methoxy hydroperoxide species. Then amines are used as the coupling partner, and copper chloride is used in the catalytic amount having dual role. One is used as a reductant and another role is the coupling platform, and phenanthrene is used as the ligand to provide the access of the amino products. In the example, we can see that protected tryptophan, phthalimide, benzopyrazole can be used as the amine handle, and this reaction can work with monosubstituted alkenes also, giving moderate to excellent yields. In the mechanism, there is copper 1. This copper 1 can reduce the alpha methoxy hydroperoxide to the alkoxy radical, and copper 1 goes to the copper 2 state. On the other hand side, the alkoxy radical then undergoes beta session, forming the alkyl radical. And now amine comes in the catalytic picture, and it does the ligand exchange with the copper 2 species, forming the copper 2 amine complex. Now there are two possibilities. One, that the alkyl radical can do the directly SH2 reaction to generate the product, or it can add to the copper 2 species, forming the copper 3 species, the intermediate 3, which on reductive elimination will give the amino product, closing the copper cycle. Having discussed the hydrogen and heteroatom incorporation in the dealkynylation strategy, now I will move to the carbo functionalization post dealkynylation, and I will discuss first the alkynylation. In the dealkynylative alkynylation, the alkene undergoes activation using ozone and methanol, forming the alpha methoxy hydroperoxide, which is reduced using ferrous sulfate, and nitrostyrene is used as the alkylating reagent to generate the desired olefin product. The reaction works well with the monocyclic natural products, bicyclic natural products such as nutcatone, and acyclic natural products as dihydroleucine, giving moderate to good yields. In the mechanism, at first the alkene undergoes activation using ozone and methanol to the alpha methoxy hydroperoxide, which can be reduced using ferrous form to generate the alkoxy radical, the intermediate 2. The alkoxy radical pushes back and kicks out the alkyl radical, which can now add to the nitrostyrene, forming the more stable benzylic radical. The benzylic radical then falls back and kicks out the NO2 radical, forming the desired alkene product. After the alkynylation, it's time to discuss the alkynylation. In the alkynylation, similar to the alkynylation, at first the alkene undergoes activation using ozone and methanol to the trapped Krieg intermediate, the alpha methoxy hydroperoxide, which can be reduced using catalytic amount of ferrous sulfate, and vitamin C is used as the external reductant, and alkyne sulfones can be used for force of the alkyne to generate the alkynated products. So reaction works well with monocyclic natural products, bicyclic natural products, and acyclic natural products, giving moderate to good yields. In the mechanism, the ozone activates the alkene, forming the alpha methoxy hydroperoxide. Now the Fe2 can reduce it to the alkoxy radical, itself going to the Fe3, and vitamin C can reduce back the Fe3 to Fe2, closing the metal catalytic cycle. Now the alkoxy radical forms the alkyl radical via the beta session method, and followed by addition of the alkyl radical on the alkyne to generate the vinylic radical. In the intermediate 4, the vinylic radical then pushes back and kicks out the sulfone radical, forming the desired alkyne product. Till now, I have discussed the strategies where the ozone is used as the activator of the alkene. Now I am going to use the ozone-free Isayama-Mukayama peroxidation followed by hydrodealkynylation strategy. So what's the significance of this methodology? For that, at first I will discuss the disadvantages of ozone-mediated hydrodealkynylation. And the first disadvantage is the ozone incompatible alkenes. Subalkenes like alkenes with electron-rich aromatics, having high steric hindrance, or having internal electrophiles, or allylic alcohols doesn't work well with the ozone mediated strategy. To address this problem, the IMP methodology is the only solution. And the another point to be noted is the different reactivity. For example, if alpha pinene is subjected to the ozone mediated hydrodealkynylation, we can get the excess of this aldehyde, via this four-membered alpha methoxy hydroperoxide intermediate. On the other hand side, the IMP hydrodealkynylation will give access to the keto product via the six-member sila peroxide intermediate. So how does intermediate forms? To discuss that, I am going to discuss the IMP hydrodealkynylation strategy in brief. So at first the alkene undergoes activation and forms the sila peroxide species using the catalytic amount of cobalt-2 and triethylsilane in presence of oxygen. Now this sila peroxide is isolated and subjected for the next reaction where it is reduced using ferric sulfate and thiol is used as a head reagent in catalytic amount, generating the desired hydrodealkynylated product. The reaction works well with the alkenes having internal electrophiles, allylic alcohols. It can act on the fused bicyclic 3-carene, giving the acylic product, and it gives the keto product from the alpha binding, what I have discussed earlier, giving moderate to good yields. In the mechanism, at first, the ferric species, which is in coordination with the solvent methanol, can undergo solvent displacement via thiol, forming the Fe3-thiol species. Now, the Fe3-thiol species on proton elimination forms the bond, the ferric thiolate species. Now, the ferric thiolate species can undergo homolytic cleavage, forming the ferra species. On the other hand side, the sila peroxide is synthesized from the alkene using IMP methodology that is reduced by the Fe2 to the alkoxy radical, and Fe2 forms the Fe3 species with OSI83. Now, methanol can close the catalytic cycle, regenerating the Fe3 active catalyst, or in presence of thiol, it can directly make the ferric thiolate species and take the reaction further. Now, the alkoxy radical can undergo beta session to form the alkyl radical, and the alkyl radical can take the hydrogen atom from the thiol, forming the desired hydrodealkynylation product. So this methodology is not only limited for the functionalization reaction, this is applied for the various natural product synthesis also. One of the example is this tricyclic ketone known as -2-pupukianone, which can be synthesized from a bicyclic gamma keto ester, and the bicyclic gamma keto ester is synthesized from this corresponding alkene. The alkene is first subjected to the hydrodealkynylation standard conditions, giving the hydrodealkynylated product with 78% yield. Previously, this transformation was done using 6 steps having 28% overall yield. So this transformation shows the robustness and the advantage of the dealkynylation methodology. And the gamma keto ester can be treated in several steps to synthesize the desired natural product. Another natural product is this heptacyclic vilmoraconitin, which can be synthesized from this bicyclic gamma keto aldehyde. And the bicyclic gamma keto aldehyde is synthesized from this tricyclic alkene. The tricyclic alkene is first activated using ozone and methanol, forming the alpha methoxy hydroperoxide and aldehyde. The alpha methoxy hydroperoxide then undergoes dealkynylation via reduction using ferrous sulfate and HAT using 4-methoxythiophene, forming the dealkynylated product in 77% yield, which can be converted to the desired natural product after several steps. Not only natural product, but also various drug molecules can be synthesized using dealkynylation strategy. One of the example is this isomoracin C, which is a 5-lipoxygenase inhibitor. So this isomoracin C is synthesized from the styrene derivative, and the styrene derivative can be synthesized using the alkynylation strategy using this commercially available olefin. So this olefin is subjected to dealkynylative alkynylation conditions using the mentioned olefin to give the styrene derivative in 56% yield and very high E by Z ratio. And after several steps, the desired isomoracin C can be synthesized. So now I will summarize my presentation. In the summary, we have discussed about the alkenes first. Then I have discussed the activation methodology followed by reduction and beta session to generate the alkyl radical. And the alkyl radical then can be functionalized in various methods. In the functionalization, I have discussed about the hydrodealkynylation, oxodealkynylation, thiodealkynylation, halodealkynylation, aminodealkynylation, dealkenylative alkynylation and alkynylation, and lastly, the ozone-free IMP hydrodealkynylation. Moving to the future outlook, one of the major problems of this methodology is usage of stoichiometric amount of metal reductant or catalytic amount of metal reductant with stoichiometric amount of external reductant. To address this problem, I am proposing the radical polar crossover. So in this methodology, the alkene will be activated using ozone and methanol in the first step. Then the Fe2 will reduce it and itself going to the Fe3, and it will form the alkoxy radical that on beta session will generate the alkyl radical. Now the alkyl radical can be added to styrene derivatives forming the benzylic radical. Now the ferric species can oxidize the benzylic radical to the benzylic carbocation, itself going to the Fe2 form, closing the iron catalytic cycle, and the benzylic carbocation can be trapped using various nucleophiles. So after discussing the dealkenylative strategy and giving my view on the presentation, finally, I would like to tell thank you to all, and especially Mahesh Bhaiya for allowing me to present in his platform. Thank you.
Nice presentation, Subhayan. And nice PPT, by the way. Very nice PPT. If you enjoyed this session, don't forget to like, share, and subscribe. We'll meet you in the next episode, next session. Thanks for watching.